Alright, let's talk about some alkyne mechanisms. Alright, so the first reaction we want to look at is something called dehalogenation, and it is going to be building off of a previous reaction you should know from the last unit, which was alkynes. First, we take a regular alkene and we do the halogenation reaction to it to get the trans dihaloalkane. After we do that, we do the new reaction, which I'll show you now. You use NaNH2 in the presence of ammonia, that's liquid and cold, and you suddenly have a triple bond. Alright, so let's try to understand where that triple bond's coming from and what happens to these bromines over here. Okay, so start off with our molecule once again like this. And you've seen that I've drawn in the so-called invisible hydrogens. The reason you need to do this is because they're actually pretty important for this mechanism. For those of you who are in 307, you're doing a unit on alkenes and alkynes right now, so you probably don't need to know this mechanism, but I'm going to show you the mechanism anyway because that sort of guides you as far as what's happening in this reaction. Okay, the other thing that needs explanation is what is going on with this NH2 anion and this Na cation. Okay, so remember we added the NaNH2 into our solution, and, well, you can't add it directly, the NH2 anion that is, so you typically need to add it as a salt. So the salt we have is the NaNH2. And when you add that to a solution of, say, liquid ammonia, it dissociates into ions. It dissociates into positive sodium ions and negative NH2 anions. And the reason that we actually want this is because this molecule over here, this anionic species, is a pretty good base and a decent nucleophile. So the way that most people think about it, or the metaphor that I've heard the most often, is that you need to think of this NaNH2 as a pen. So we want to be able to write with our pen. What's the first thing we need to do? Well, we need to take the cap off the pen. The cap is considered this sodium over here, and when you add this molecule to solution, the so-called cap comes off, and you now have the pen available to use for writing, or in this case, using it as a base. So again, we need to add this as a salt to our solution because we want a good base, and once it's in solution, it breaks up into ions, and we could use this anionic species. Okay, so let's take another look over here. So with those hydrogens drawn in, now we could actually do our reaction. So the first thing is that we have the attack on the hydrogen. So I'm sort of deleting things because I don't want to give you too much information too soon. So this is called an E2 elimination. You don't have to worry about it so much right now, but it turns out that that trans setup, or that anti-setup from the halogenation, is actually pretty important here. So important that I've had to do a bond rotation to actually get this Br over here and this H over here. Again, don't worry about that so much. Think big picture. The big picture is that the base is attacking the H. Remember, you can't have an H with two bonds to it, so as this bond forms, this one needs to break. Where do these electrons go? They actually go into forming a pi bond along here. A little strange, yes, but an idea that you'll have to get used to. Now, once again, this carbon over here can only have 4 bonds. If the pi bond is forming here, that is 5 bonds to carbon. The pi bond is 2, this is 3, that's 4, that's 5. So one of these 3 bonds over here to this carbon needs to break. The carbon-carbon bond is pretty strong, it's not going to break. The CH bond won't break because you don't usually see H- anions in solution. That's very uncommon. But what we do see pretty often is Br- anions in solution. And we'll look at that a bit more later, but for now, just take for granted that the bond that's going to break is this Cbr bond. And after that bond breaks, the result of our arrow pushing is that we get the formation of this double bond over here. And now we don't have to worry about the wedges or dashes anymore because we've essentially lost them due to this double bond. Okay, and the Br that comes off is going to be hanging out with the positive sodium that was still in our solution, and we've generated NH3 by the acid-base reaction here. And if you remember, NH3 is our solvent, so we could pretty much not look at that anymore. Okay, so what's the next step in this reaction? Well, remember, we're trying to go from the dialkyl halide, which looks like this, to the alkyne. And so far we're only at alkene. So you might be thinking, all right, how do we go from this species to the alkyne? Well, you essentially just do the same thing once again. So we take this species that we have here, and we once again take the NH2 as a base and attack it here. And once again, we're forming 2 bonds to hydrogen. One of these needs to break, and the electrons once again go into this region here. Since we already have a double bond, we're going to develop a triple bond. And since you can't have that many bonds to carbon right over here, again, a bond is going to break. And it's going to be this CBr bond because it's very unfavorable for the CC bond to break, and very favorable for the CBr bond to break and give Br minus in solution. And I should add that there should be another sodium that was essentially the cap of this pen over here. Okay, and if we draw what happens after this arrow pushing, what we get is this. Our alkyne, more ammonia that we've formed that's already our solvent, and these ions basically pairing up. Remember, our original reaction started neutral, and these reagents were neutral. So at the end, we need to conserve charge. So at the end, this is neutral, these are neutral, and the net charge of this group over here is 0. So we've preserved charge just fine. Okay, so let's look at this reaction one more time, slightly differently. Say we have an alkene, such as this one, and we do the halogenation reaction on it, and we're going to generate this. Okay, if we want to do a similar reaction that we just learned, we have the NaNH2 and ammonia that's cold once again, but this time we need to add water. Okay, why do we need to add the water? Well, we could take a look at that mechanism once again and try to figure that out. So let's look at it a bit quicker this time. So again, the NaNH2 dissociates in solution to Na plus and NH2 minus. This comes in as a base, does this elimination reaction to form a double bond here, and these are the counter ions. I've left out the NH3 because that's just an excess anyway. Okay, and then once again, what happens is that the NH2 comes in, attacks this hydrogen, and forms the triple bond, and we get this. So that's pretty similar to the reaction we just saw, where we formed this. Note here that it required 2 molecules of NaNH2 to do this transformation. Over here, it still took 2 molecules of NaNH2. Okay, but remember, typically when you're doing an organic reaction, you want to push your yields up. You want to have your reaction go to completion. So usually use more NaNH2 or more base than necessary. So here we would need 2 molecules of base for every molecule of our dihaloalkane. Usually chemists will use 3 or 4 equivalents just to make sure the reaction goes all the way. But what happens if we use just 2 equivalents for this reaction here? The difference being we've formed a terminal alkyne, which means there's an H bonded to the alkyne, versus an internal alkyne, which looks like this, where the triple bond is surrounded on both sides by other carbons. So let's do this thought experiment. Suppose we now have 2 molecules of our original dihaloalkane. And suppose that, because we just figured out, we need at least 2 molecules of base for every molecule of our dihaloalkane. So say we have a solution where we have 4 of these and 2 of these, so the ratio is still 2 to 1. We perform our reaction, and what do we get? we get this. Now, don't get scared of this. It looks complicated, but I'll tell you it's really not that bad. So we had that 4 molecules of ammonia that we're going to get, because whenever an acid-base reaction takes place in here, remember the NH2 just grabs a hydrogen, and it's going to go to NH3. These are the counter ions that are present whenever, well, 3 of these come from the NH2, and 3 of them come from the chlorines over here. You'll see that 1 chlorine is still attached. So you'll see that our reaction, remember our desired product, was this. What we have here is an intermediate that we wanted to go further to an alkyne. So this is a unreacted intermediate. And over here, this is, well, deprotonated alkyne. Remember, we wanted the CH bond on this. It is actually not there. It's just a lone pair on the carbon. So what happened here? Well, try to think about it for a little bit and figure it out yourself. Pause the video, go through the mechanism, and see what could happen. Okay, I'm going to assume you gave it a sort of attempt, but what you should realize is that this is what's happening. You have the terminal alkyne that we formed at the end of our supposed mechanism, but you also are working in NaNH2. And remember, NaNH2 is a good base. So what could happen is the base takes this hydrogen and you're left with this anion. Now, since this NaNH2 is consumed, there's no base to actually work on this and create the triple bond. Instead, it worked on this. So what do we need to look at? Well, first of all, let's explain this acidity. Let's try to figure out what was happening with our molecule. Why is this alkyne so acidic? Well, if you'll remember, the whole idea of alkynes is that there's a triple bond here, so the hybridization at this point is sp. Now suppose we did an acid-base reaction, we took this H off, what you'd have is this resulting anion, which is sometimes called an alkynyl anion. So what do we need to know about that? Well, several things. If you remember your hybridization, this sp orbital is 50% s character and 50% p character. Remember, with the s orbitals, they have more electron density found closer to the nucleus, so they're better able to stabilize a lone pair. The other thing you need to remember is that a stable conjugate base means the conjugate acid is relatively strong. So we know that this is pretty stable. It's stable because you have a orbital with 50% s character holding a lone pair. Now we know this alkynyl anion is relatively stable. That means our alkyne is relatively acidic. So what does this tell us in regards to the reaction that we're doing? Well, if we need to account for this, if we need to account for the fact that the base is instead going to deprotonate this before this reaction happens, we need to make sure that we use excess base. So we need to use at least 3 equivalents of base when doing the reaction on an internal alkyne, a terminal alkyne. The other thing we need to remember is that, what is this water doing? Well, if you add excess base, then you keep forming this product. But if there's excess base present, this is going to be deprotonated. So all your product after the reaction is going to be this. Then use the H2O. And what does that do? Well, it simply just puts the H back on. So to speak, it puts the cap of the pen back on. So this reprotonation occurs and you're good. The reason you don't need to use the H2O in the internal alkyne reaction is because there's no H connected to the triple bond. So just to recap, if you have an internal alkyne, use at least 2 equivalents but no water necessary. So that was the first example we looked at. But if you're looking at a terminal alkyne, use at least 3 equivalents, then water to reprotonate. Okay? This entire series of arguments is actually pretty subtle, so I recommend, if you didn't understand it, going back and watching this again. Okay, that said, let's move on to the next type of reaction that's important to look at. And it's even more similar to the ones you've looked at in alkenes. And that is excess halogenation. So here, instead of having an alkene, we have an alkyne, and we react it in excess Br2, and we get this product. So let's try to figure out what's happening in the mechanism. Well, start with your standard, I guess, carbocation intermediate. In this case, actually no, I'm looking at the wrong one, sorry, because this will form a bridge. Hold on a sec. Okay, yeah. Start the mechanism as you pretty much do every other time with the alkene. In this case, just pretend that the triple bond is actually a double bond. So as that Br-Br molecule comes closer, the polarization occurs. This becomes partially positive, this becomes partially negative, and the nucleophilic triple bond will now attack. The result is that you get, as usual, a bridge. Now you can't put wedges or dashes here because remember you're off a sp2 hybridized carbon, so there is no wedge or dash. It's just going to be regular lines. Okay, and that is your bridge. Now once you've done that, as usual, have the bromine attack on the less substituted, well, more substituted side because that has the stronger partial positive charge, and you'll generate this. Now here we don't have to really worry about that because this is a symmetric species we've formed. In general, unless you do this reaction on a terminal alkyne, you don't have to worry about which side the attack occurs. Okay, and then after that, once again, you've seen this before on alkenes, so you should know what happens. What happens is the trans addition or the anti-addition through the bridge intermediate that we just did, that gets you this product. So that you should be pretty comfortable with. Let's look at something a little stranger. So this reaction is called Geminal halogenation. So it looks like this. Once again, you've seen these reagents, except this time we're doing it to a triple bond instead of a double bond. So HCl and CCl4. You might expect that this is going to look pretty similar to the hydrohalogenation mechanism. So this is what I meant to copy before. Start with your standard carbocation intermediate. So pretend that your triple bond is the same as a double bond and do what you'd usually do, which is nucleophilic attack from the triple bond onto this H. You form 2 bonds here, so you need to break one. The result is that you generate this, which looks sort of strange if you haven't seen it before. It is a carbocation directly on the double bond. Alright, don't get too upset about that. You just pretend that the double bond isn't there and that you're doing your typical hydrohalogenation reaction. So the chlorine anion comes back and it attaches there and everything is good. And just like before, what do we do next? Well, the exact same thing you usually do. You do it again. So another molecule of HCl comes on that attacks, well, the double bond attacks the H. 2 bonds to H means you have to break one of them, so the lone pair is going to go onto the Cl. And now, this is a little tricky. This is new territory. So there's 2 possible carbocations you could form. One where the carbocation is formed on the right-hand side, and one where the carbocation is formed on the left-hand side. We need to choose which one of these is more stable. And technically they're both secondary, because this is a secondary carbon, and this is a secondary carbon. But you should remember, one of the most important things in this class is, of course, resonance. So what can happen, or what will happen, is that there's a lone pair on the Cl that could come down and form a pi bond here, and that's going to delocalize this positive charge. So you'll actually find that the much more stable structure will be the one where the carbocation is formed on the carbon bearing the Cl. As a result, the resonance stabilization makes the Cl anion attack on the same carbon that the previous Cl was on. Okay, so the big idea here is that this reaction is relatively selective. So before, when you did this, you could have tons of carbocation rearrangements, but because the positive charge forms on the same carbon that has the Cl, it's very unlikely that you'll get a rearrangement with this. So there's a rather selective reaction that, strangely enough, has a carbocation intermediate. You know, there might be some examples of reactions where there is a rearrangement here, but you need a big justification to have movement, I guess, of your carbocation. All right, let's look at one more. So this might be the most important reaction, and it requires you to sort of understand what was going on with that first one with the NaNH2. So here we're again going to look at the alkyne acidity, and we're going to do a base-mediated SN2 reaction. So again, you don't need to know the mechanism for this yet if you're just studying alkenes and alkynes, but I'm going to show it to you just so you understand what's happening. So this time, if you have an alkyne, like so, in the presence of a haloalkane, then in the presence of NaNH2 and a solvent such as ammonia, you're going to get, well, let's take a look at it. So mechanism-wise, what do we have going on? Well, the first thing is that, once again, the NaNH2 is going to do what it does best. In solution, it's going to dissociate into ions, so this sodium plus and this NH2 minus. And since the alkyne we've discovered is relatively acidic, it is going to do the acid-base reaction on that and generate this. Okay, so what do we know about alkynyl anions? Well, they have a lone pair in an sp orbital, so that is relatively nucleophilic. Okay, so now we have a good nucleophile. Well, what I'm also going to tell you is we have a decent electrophile. So let's look at what's remaining in our solution. We have this alkyl halide, and we have this over here, this relatively good nucleophile. Okay, so let's go into a little more detail about what I was telling you earlier. So what happens when you add a strong acid like HBr in water? Well, you get this acid-base reaction that's happening, and it goes to Br minus and hydronium ion. Okay, and again you have to remember that HBr is a strong acid, and this is a basically irreversible reaction because of that fact. So again, strong acid has a stable conjugate base, and the reason we care about that is that Br minus is preferred to be generated in solution. So Br minus will wants to exist. We'll say it that way. If you have a species like this, the Br wants to be in this form because it has a complete octet and various other reasons. It's relatively electronegative. It wants to exist. This reaction has a fairly large equilibrium constant, so you know that it's fairly likely to occur. Same thing is true over here. This Br is attached to this alkane, but it would prefer not to be. It would prefer to be Br minus instead. So what you have is what we call SN2. And it's going to look like this. You have the alkynyl anions lone pair attack the carbon that is attached to the Br. And remember, because there are 2 more CH bonds here. If you're forming a 5th bond to carbon, you need to break one because carbon can't have 5 bonds. So as this attaches here, this bond needs to break. And this bond is actually preferred to break because, again, Br- is actually happy in solution existing as Br-. So Br is what we call a great leaving group. And you'll see the word leaving group used in the next unit when we start talking about substitution and elimination in more detail. So the reason why this reaction in general is particularly useful in synthesis is now you found one of your first ways to go from, well, 3 carbons to now 1, 2, 3, 4, 5, 6 carbons. So this is a method of elongating your carbon chain. Okay, let's take a moment to recap what we did. So these are the reactions we just looked at. Dehalogenation, the first one is when we had an alkene and we used the halogenation to first create this species found here. So I'm actually going to add that to the table. So first we used the Br2 to go from alkyne to alkyl halide, and then after that we used this base to do our E2 elimination, and in the end we created our alkyne. The other thing we found out was that 2 equivalents of Na and H2 were needed for internal alkynes, and 3 equivalents of Na and H2 were needed for terminal alkynes, followed by water for reprotonation. Again, this is pretty subtle, so I would say look back at this if you didn't understand it. And this pertained to this reaction. The second one we looked at was excess halogenation. That's when we had the alkyne and we reacted it completely in the presence of some, well, halide. And we formed the alkyl halide. We actually formed a alkyl halide that had 4 different halogens attached to it. The third thing we looked at was geminal hydrohalogenation. The word geminal refers to the fact that the final product that we created, such as this, the halogens are bonded to the same carbon. So this Cl is geminal to the other Cl. That's what we mean by that. And lastly, we looked at the base-mediated SN2 reaction, which is very useful in synthesis because it allows us to elongate however many carbons we currently have. If you want to work some problems using these reactions, there should be some on the synthesis video, which will be up briefly.